Okay, let's do one more. This is a really nice max-min problem. This one is a minimization problem. I got the idea a number of years ago when I was in New Orleans, up in a hotel looking down on the Mississippi River. And I noticed that there was a tugboat that was pushing a barge upstream. So it was pushing the barge through the water, let's say with the speed V. That's the speed through the water, okay? That's the speed at which they see the water passing by them, okay? And it's going upstream, so the water is coming this way, let's say with the speed of VC. C stands for current, okay? So that's the current. So let's suppose that this barge was being pushed from, say, point 0 up to point P, a distance of P. And my question that formed in my mind was, I wonder what speed should that tugboat push the barge so that it gets from here to here in the minimum amount of energy, okay, the minimum amount of work. And so I remembered from physics that work, or the energy, the two are synonymous in this case, is equal to the force exerted, which would be the force to overcome the friction, times the distance. And the distance in this, let's just say the distance here for D. That is force times distance. And also, I remembered that the force, in this case, the only one we're really assuming is the force due to friction, is, for slow speeds, is proportional to your speed, to the speed through the medium. So if you're paddling a boat and you have your hand out in the water, like here, your hand is out in the water, you feel the water against your hand, and if you go faster, then the force of the water against your hand doubles and things like that. So if you go twice the speed, the force that you're having to push against the water, or if you have your hand out the window, the force due to the air resistance is proportional to your speed. For slow speeds, that's about right. So given those two things, we can already see what the answer would have been if you were moving across the lake. Because if you're moving across the lake, then the distance is set, and all you want to do then is to minimize the force, and the way to minimize the force is by minimizing your speed. So all you do is you cross the lake as slowly as possible, and that's going to get you across the lake with the minimum work. But things become more complicated when you're going against a current. Do you see why? Because let's just think of an example over here. Suppose that you were in a river and you were going upriver, either swimming very fast or boating or whatever else, rowing at, say, 5 miles an hour. That's the speed with which you're going upriver. And say the current is coming back at you, so this is your V right here. And this is the speed of the current, let's say is 3. Okay, and say you wanted to go 8 miles upriver. Okay? Well then, let's just think about it. How much work have you actually done? You just say 5 times 8? No, that's not right. That would be the case if you were on a lake. But you're not on a lake, you're going against the current. So effectively, you're going at 5 miles an hour through the water, but you're going for quite a while. How long are you going for? Well, let's think about it. The amount of time in the water, distance is equal to rate times time. So time is equal to distance over rate. So if you think about this, your time in the water is gotten by taking this distance right here and dividing that by the speed with which you are moving upstream. What's the speed with which you're moving upstream? You're going through the water at 5 miles an hour. The water's coming back at you at 3. So you're going upstream at 5 minus 3 miles an hour. That is 2 miles an hour. 8 divided by 2 is 4 hours. So you're in the water for 4 hours, and all those 4 hours you are swimming 5 miles an hour. See that? So your, let's call it effective distance, your effective distance is 20 miles, because as I say, you're in the water this long. There's the amount of time you're in the water. All that time you're moving this fast, and so you're moving at 20 miles. You're moving effectively 20 miles through the water on this particular swim. Okay, so the point is, this effective distance that you're having to move through the water depends on how much faster you're moving than the water is. If you're moving at let's see, this is at 10, let's say at 13, or let's say at 11 miles an hour. Let's just say you're moving at 11 miles an hour. If you're moving at 11 miles an hour, 11 minus 3 is 8. 8 over 8 is 1. Then you're in the water effectively just 1 hour. And so 1 times 11 would be effectively 11 miles that you had swum. Okay, so if you swim faster, you're effectively not swimming as far. If on the other hand, if you were to swim at just a little bit over 3 miles an hour, 3.001, well, now what happens? Now you're barely making any headway at all. So 8 divided by 1/1000th would be 8,000 hours, and so 40,000 miles. I mean, the point is you're going a long distance here because you're barely going faster than the current. So those two things are in opposition to each other. They're in tension. Okay, if you go too slowly, then your effective distance is going to be really large. If you go too fast, then the force is going to be too big. So you want to find that optimal choice of velocity through the water, which minimizes your energy. Okay, that's what makes this problem interesting. So let's see if we can figure it out here. So let's say that the work is equal to your force times this effective distance. How much water have you actually pushed past? And the force is K times V. And the effective distance, same as here, is what you get by taking this distance here, which would be P, make it a little bit better. You take P, you divide P by the speed with which you're going through the water. You divide P by the distance with which, the speed with which you are moving up the bank, okay? So you're moving up the bank, up the shore, at a speed of V minus VC. See that? There's the distance that you're covering. There's the speed with which you're going upshore. There's the amount of time in the water. This right there, there was your amount of time. Here's your amount of time in the water right there. So all that amount of time in the water, that's this whole thing here. All that amount of time in the water, you are moving at the speed right there. So here's your amount of time in the water, all that amount of time, this is how fast you're moving. And so you multiply rate times time, and there's your effective distance. That's basically how much water you've pushed past. So there it is. Now, that's the hardest part of this problem, is just thinking through this. Okay, now we can discover what choice of V is going to minimize that work. So let's do it up here. Here's the amount of work. I'll write it as work V is equal to K and P are both constants, so I'll bring them out front. And we're left with V times V divided by V minus VC. Okay, look good? So there it is. And so let's go ahead and take the derivative. And we'll just keep the constant out front. Here we have to use the product rule, the quotient rule. You take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. There we go. So let's see what we get. We get Kp. If we multiply this out, we're going to get 2v squared. Here we have a v squared, so 2v squared minus v squared is just a v squared. And then here we have 2v vc. 2v vc. That's all on top. All of this is still on the bottom. And so we want to know, when will this be 0? Again, just think about it physically. What are your options? If you move too fast through the water, then this force becomes very, very big, and if the force becomes very, very big, the amount of work is going to be big. So if this is your velocity through the water, if you move too fast, it's going to go up. On the other hand, if you move too close to the speed of the current, say this is the speed of the current right there. As you get closer and closer to the speed of the current, you're going to be in that water for a long, long time, and so your effective distance gets to be really, really big, and so the amount of work goes up there too. So if you were to actually graph this function, go ahead and put in some values for K and P and VC there and graph it, and you'll actually get something that looks kind of like this. And so what you want to do is you want to find out what's that minimum right there. And so we're almost done with it. Let's go ahead. We can factor a V out of this. And if you set that equal to 0, you notice it's going to be 0 either when velocity is 0, which makes no sense. That would be less than the velocity of the current, so that's physically impossible. And then the other one that does make sense is when V is equal to 2Vc. So just to fill it all out, V minus 2Vc is equal to 0. So V is equal to 2Vc. Isn't that cool? In other words, you should be pushing through the water at exactly double the speed of the current. So if the current is coming this way at 3 miles an hour, that means you're pushing through the water at 6 miles an hour. Since you're pushing through the water at 6 minus 3 means you're moving up the bank at 3 miles an hour. See that? So whatever speed you see the current moving along the bank this way, you should be moving upstream along the bank at exactly the same speed. So I keep this in mind when I kayak and so on. If I want to try to minimize the amount of energy, I just kind of watch to see how fast the current's moving. If I'm going upstream, that is. Going downstream, the way to maximize is just to float. But if I'm going upstream, then however fast the current's going this way, I just move upstream at exactly that same speed. By the way, so this is a really nice calculus problem. I have a counterpart of this called, which basically allows for the fact that the speed of the current is changing as you go. And so then what speed should you choose as your constant speed upstream if you have a variable speed of the current? And that becomes what's called a differential equation. Which is more Calc 3 or Calc 4 material. Or even Calc 2 for that matter, I guess. Anyway, but that's kind of cool. So anyway, kind of a cool problem. This is also why you've maybe heard it explained that if you are ever close to shore and you here's the shore and you're trying to swim in towards shore and you feel that there's a rip current that you're pushing against in order to get into shore, which happens here in the Great Lakes quite often, then the best thing to do is not to try to swim against it, because then you're running into this problem. Your effective distance is going to be very large. Instead, just go ahead and move parallel to the shore, even though it's going to be pulling you out while you do it. And once you get out of that rip current, now go ahead and come back in, and your overall distance will be much less. Okay, so this is another problem that it has very nice application to it, and it's one that, as I say, I've published before. It's been published in a couple different ways. The Mathematical Horizons of the MAA has a Horizons. MAA has a copy of it, all written out with pictures and diagrams and everything else. I think it's called Barging Ahead. Barging Ahead, optimizing a trip upstream, something like that. Optimizing a trip upstream or upriver, something like that. Check it out, should be able to find it, and it has my name on it, Tim Pennings. And anyway, it's kind of a nice problem. So anyway, so very nice. So there now you've had a lot of good examples of how you can use calculus to find optimal solutions of things, and this basically covers really all there is to cover about the use of derivatives. And so now in the next lesson we're going to get into the whole second topic of calculus. Remember what I said was, here's functions, and then we use limits, and all of this stuff was derivatives and slope. And now we're going to get into the second tower, which is area under a curve. So that's coming up. Good stuff. Okay, very good.